Hello everyone. Today we're going to discuss about the Lab 1 Introduction to Digital System Design of our CSCE 312 Fall 2022 course. In this lab, we will first discuss about some general lab instructions, and then we will discuss about the problems that we have to do for our specific lab. Firstly, about the general lab instructions, first we discuss about the learning method. In this course, you will learn by doing exercises and by designing systems. You will also learn how to learn from additional sources other than textbooks. System design is more of an art than science, which is best learned by observing work of other designers and looking over reference design. Software often documents and reflects the design of the system. For the lab assignments, you will be specifically asked to focus on the subset of the topics that you can learn from the programs that will be provided to you by the instructor and the TA. However, additional topics can be learned by completely analyzing these given programs and progressively developing advanced skill and adopting and applying those throughout the rest of the course. As the lab class proceeds, we will progressively guide you towards those additional topics. Therefore, read the complete program. This is a must that are provided even though you may not understand them correctly or entirely at this point of time. By doing so, you would at least become familiar with how code segments and functions look like. And when time permits, you should do additional research using search engines like Google, software manuals like man from Linux Unix environment to understand and rationalize them. Instructions regarding these are provided in the next section. Your level of programming skill and knowledge, and most probably future job prospects, will depend a lot on your motivation to go this extra mile to learn additional topics beyond the immediate need of doing assignments. Resources that you may need in this course are wide range. So for starters, we would ask you to visit the CS Help Desk webpage. We have provided you with the link. Here there are a lot of tools and tips and techniques to access the services and the resources that you have at our department. Firstly, you will need to know how to compile C programs. We have provided you a short description in the Appendix A. Also, there are links of detailed examples. All our programs will be evaluated at the CS computers that we have available at the compute and Unix systems. So you might need CS VPN access to access them from home. CS department help pages can be a good resource page. You may want to use your Linux machine from a different operating system like Windows. For that you have PuTTY, MOVA Xterm, VS Code, etc. Then you have different way to transfer files from Windows Mac Linux machine to CSC server. For example, Windows users can use WinSCP tool. Mac or Linux, where you can use terminal, you can copy some directory to the destination directory of your unix.csc.tamu.edu machine. You need to execute the following command. Here you are using the SCP program with -r option that it shows recursively, that is you can copy an entire folder or directory. So here you are copying the source directory to the unix.csc.tamu.edu using your own net ID, and you will copy that to a destination directory. If you do not provide a destination directory, that would be copied to some home folder. To access the manual page, which is an interface of the system reference manual in the Linux Unix console, you have to type man followed by the Linux system call name. For example, here if you see, we have a program called ls which lists all the file, but maybe you didn't know what are the options of ls is. So you can type man ls, that will give you the details of the ls content. So for example, here we can see ls is list directory content, and all the options that you can see, for example -a or all, something like this, and then you can read them to understand the details of the function that ls takes. So this is only available for the system calls of the that is already implemented in Linux, or all the functions that have their own manual entries. But if there isn't any, then you would not be able to find the man for that. For example, if I just write here like man my function name, it is should not be there, so there is no manual entry for my function name. Specific instructions. For specific instruction, you need to follow this carefully throughout the lab. That is, you need to submit your answers of all the lab assignments using a soft copy. So this soft copy might have some PDFs, it might have some code, it might have some PNG screenshots, maybe text file, etc, etc. You have to zip all of them in a single zip file and then submit that zip file only at Canvas, and you must do it before the deadline to get the full marks. Some of your homework might require hard copies. If that's the case, you will be informed, and you have to submit the worked out problems on paper to your instructor or TA. The late penalty policy is put in the course syllabus. For each problem, you have to find out the sections where you can see activities to do, and this will contain the problems. And you have to answer all the sub problems under activities to do, and this should be turned in as a PDF format since we require to read this. For some problems, you have to submit text and C files in addition to these PDFs. You may use your own machine to compile and test codes. However, to ensure fair grading, all assignments must be shown to work in CS department's Linux Unix system that is available for you to access. Assignments might come with associated program code, text, etc. Always make sure to check your assignment folder or the lab class folder for those codes. For example, in today's lab, you will see some source files uploaded in the assignment. The lab 1 quiz section, you will see some files already assignment as the lab1 source.zip file. Download this and use those codes inside that. A lab topic might span for more than one lab class. So you will see if there is one lab topic that is spread for more than one lab class because of time constraint. So these are the instructions that will be followed throughout all the labs. Since this is the first lab class, we are explaining this. And now we will move on to our specific lab topic for today's lab class, that is chapter 2. In chapter 2, we have titled it as Introduction to Digital System Design. You will learn the importance of low-level system design for solving real-life problems. This will immerse you in a program context which will require you to apply the theoretical concepts taught in the class. This will help you to develop basic skills needed to become a device-level system developer and digital system designer. While going through this chapter, concentrate on developing a good understanding of the problem context, as it is a fundamental requirement to become a skilled system designer or application developer. You will have 2 weeks to complete this assignment, and you will need CSCE as the required tool. Our primary objectives for this lab class is to know how numbers are stored in a computer system, how we can relate computer programs to a given real-life application, how we can design C code to solve real-life problems using Boolean logic or Boolean algebra. Specifically, we will learn to know how to construct right logical expression and use them. We will learn to optimize the code for a real-life embedded system with programming tricks that apply to Boolean logic concept, tools, and low-level C programming features. To appreciate the need to learn more about hardware, we will learn the hardware-related knowledge, why this is necessary to develop useful systems and the real-world applications. Finally, our last primary topic is to learn how to design digital systems, especially for safety-critical applications. The secondary topics will include useful C functions that will help us to understand a platform's data representation, how a data is represented in a specific platform. We will learn to use GCC compiler in Linux environment. We will learn the coding patterns, style, some jargons, terms that are used in the trade. We'll also try to learn standard C library and Linux specific system functions, difference and relationships between them. So these are our objectives for this lab. For the problems, we will see we have 100 points in total that we can achieve, and there are 5 problems. The first problem, problem 1, allows you to read a C code. This code is also available in the lab1 underscore problem1.c file. But as you can see, we are using three different headers here: the standard library.h, standard io.h, and systime.h. These header files are available for your computer, should come with GCC. And there are some simple codes like variable declaration. We are checking some logic to open a file pointer. Then we are getting the time for that day, for that instant, and then we are assigning that variable to the timestamp. Here we are using fprintf function to print this line to the file pointer we just opened. This file pointer was try to open a file called lab1 problem1 underscore out.txt in append mode. That is, it will create a file if it does not exist, or it will just open the existing file and add this line at the end of the current text. So this is the first line that will be printed. These are the second, third, fourth lines. These all four lines will be printed in the same file because we are using the my file pointer, which is here. So in the first line, we will print this program was executed at what time from this timestamp. We will also print this line where we are saying that this the sizes of different data type for these machines are, and then we will print integer data type and double data type in that particular machine. So the first part is the byte length, and then we have the bit length because 1 byte is 8 bits. After that, we will print some more lines using printf instead of fprintf. This printf will print these lines in the console instead of in printing in the file. So we will print this integer, double, and short data type here, and then we will close the file pointer. For activities for getting the points of this code, you will first need to explain using less than 4 sentences, that is in as short explanation as possible. Explain what function or action the two statements marked with tag 1 and tag 2 perform. So here we have tag 1, which is int underscore variable, and then we have this f close file pointer, this line as tag 2. So you have to explain what these two statements do. Then you have to compile and run this whole program using GCC on the CS CentOS 7 Linux machine available at linux.csce.tamu.edu address. So you can access this using your own NetID, run this program, and then compile this and run this program using GCC, and you have to upload a screenshot of the output showing this was compiled and was run using linux.csce.tamu.edu. For the third part, you have to compile and run this program with GCC on CS Red Hat Linux machine, which is available at compute.csce.tamu.edu. You also have to upload a screenshot of this output. For the fourth part, when you run your code, did you get the time executed to be negative? You have to report that. If yes, you have to explain why that happened. Since time cannot be negative, can you fix this? You have to figure out a way to fix this if the time is negative and do the necessary modification. On the fifth question, you have to change the data type and variable of the variable timestamp. This is this variable here, which is a double. You have to change that and change that to long int. You have to rerun the program on both machine and see if there is a change in the value reported. If you have a change in the value, you have to report which values are correct and why is there a difference. You have to find out the structure of type timeval, which is here, this timeval structure. This is declared in the time.h library. So you have to find out how this structure is defined. You have to answer whether this is a standard C data type or is it platform specific. You have to submit your output files for all 4 runs. That is before you change your variable type and and after you have changed your variable type, and in both machines. You have to submit the corrected version if you have an output with negative time. If you submit a output with negative time only, you will lose 50% of the points for this problem. So this is the problem 1. For problem 2, you just have to write a simple C program to get the bit and byte lengths of all the C numerical data types of the following types. So unsigned int, character, car, unsigned car, short int, so on and so forth. So you have to run this program to find out what are the bit and byte lengths of these data types. Your C code file should have the name lab1 prob2.c, and it should generate an output file called lab1 prob2 out.txt. You need to submit your C code and also the output file. You can use this program as your base for the answer of problem 2. Here you have already calculated the data type size for int and double. For problem 3, we try to solve a real life problem. We are assuming that you are hired by Ford Motor Company to develop an embedded software for the new model of cars. This software executes on the main computer that sits inside the car. Your manager wrote down the software requirement specification, which is a document that gives all the requirements and all the sensors, actuators, necessary details about implementing the software. Based on these requirements listed in the document, you must develop a C program that materializes these requirement specifications. Given below is a portion of the SRS document which includes the schematic of the car's electronics and computer system. Here is the schematic. So in this part, what we can see here is there are the electromechanical world, which is the outside world. Then we have the computational world, which is what we have to design. And then again, we have the electromechanical world. The interface between this electromechanical world with the sensor input to the computational world is called input interface. So here we have all the sensors. For example, we have driver on seat sensor, driver seat belt fasten sensor, etc., etc. So these sensors convert physical states to electronic signals, and then this input interface convert these electronic signals to digital values. Our computational world will work with these digital values, and this is called decision control subsystem. This decision control subsystem will then process these digital values and set the output interface to control and convert these digital values to electronic signals to the specific actuators. So we have different actuators like bell, door lock actuator, brake actuator, etc. that will convert these electrical signals to physical movement or states. So in our document, we have 10 available sensors which can have either 0 or 1, that is low or high output. So these sensors will be connected through the input interface to the computational world. And these sensors will keep monitoring the sensor hardware output and act based on the sensor output state change. So what are these sensors? We have a driver on seat sensor, which indicates whether a driver is present. The sensor provides a logical high as output when a person is sitting in the driver's seat and low if he is not. DSBF, the driver seat belt fasten sensor, indicates whether a driver seat belt is fastened or not. The sensor hardware provides high when the driver seat belt is fastened, low otherwise. The corresponding integer variable that reflects the physical states inside the computer and programming world is driver seat belt fastened. This one. If the input interface subsystem sets this integer to 1, then the DSBF output is high. If it's 0, then the DSBF is low. And the decision control subsystem code reads or uses this variable. We have engine running sensor that shows whether the engine is running or not. The corresponding integer variable is engine underscore running. Then we have doors closed DC sensor, whether all the doors are closed or not. The corresponding integer is doors underscore closed. KIC, key in car, indicates whether we still have the keys inside the keyhole. This corresponding integer variable is key underscore in underscore car. Then we have the DLC, door lock lever. This indicates whether the door lock lever is closed or not. To close the electronic door locks, the driver must close this door lock lever. When the car's computer finds that the door lock lever is closed, it checks all other variables to assess the situation and finally decides whether to activate electronic door locks to lock the doors or not. For example, if the car keys are still inside, but the driver is not on seat, maybe has gone out of the car, then the door should never be locked even though the driver has closed the door lock lever. Then we have the brake pedal that indicates that the brake pedal is pressed by the driver. The corresponding integer name is brake underscore pedal. Then we have CM, car moving sensor. This sensor indicates whether the car is moving or not, and the variable name is car underscore moving. Then we have PS, passenger seat. This sensor indicates whether the person sitting beside the driver, whether there is a person sitting beside the driver or not. The corresponding integer variable is passenger underscore seat. Then we have high speed collision detection. This sensor detects if there is a high speed collision or not. In case of a high speed collision, airbags would be deployed. The corresponding integer variable is high underscore speed underscore collision. So these are all sensors which provide some input to the computational world. Then we have four available actuators: bell, DLA, BA, PAA. So the bell is a beeper or chime that sounds and plays to alert the driver of any abnormal hazardous situation. The global integer variable named bell is provided to the computer. If your code that implements the decision control subsystem sets this variable to 1, that is, you set your program, your C program, should set the variable of this actuator, then the output interface subsystem will read this value and turn the voltage on the electrical wire that feeds the beeper chime. As a result, the beeper and chime will start beeping. The beeper will stop when the decision control subsystem code sets the value of bell to 0. Because then the output interface will turn down the electrical voltage feeding the beeper and hence it will stop. The output interface keeps on monitoring the integer variable and acts when the integer changes its value. Then we have the DLA or the door lock actuator. This actuator locks the door. A corresponding global integer variable named door lock is provided in the computer. If you set this integer to 1, all doors are locked, and all doors are unlocked when you set the value of door lock to 0. Then we have the brake actuator. This actuator will activate the disc brakes in each of the 4 wheels if the global variable brake is set. This brake will be released if the variable is set 0 by the code that implements the decision control logic subsystem. Then we have the passenger airbag actuator. This actuator will deploy the passenger side airbag on the front row in case the passenger seat has a value of 1 and the high speed collision also has a value of 1. To operate this actuator, we have 6 requirements that we must follow. The requirements are: the bell should chime sound when the driver starts the engine without fastening his seatbelt. The bell should sound when the driver starts the car without closing all the doors. The bell should be off as soon as the conditions change to normal. That is, these 3 requirements associate some logic based on the sensor inputs that we have and based on some logical consequences. So we have one actuator bell that has some combination, that takes some combination of the sensor, and then the output of the bell is set or reset accordingly. Then we have the doors. The door should not lock when the driver has got out of the car, but the keys are still inside the engine, even though the driver has tried to close the door lock lever. Note, if the driver is on the seat and requests the door to be locked, the door must lock. So you need to take care of this. And then we have the brake actuator. The brake actuator should only be engaged when the driver presses the brake pedal. Brake should disengage when the brake pedal is released. The brake should engage only when the car is moving. When the car is stationary, the brake should not unnecessarily engage even if the brake pedal is pressed, to reduce mechanical wear and tear on the brakes hydraulic system. Then we have the passenger side airbag, which should only be deployed if there is a high speed collision and there is a passenger sitting on the passenger seat. If there are no passenger or if there are no high speed collision, then it should not be deployed. The passenger side airbag should not be deployed in case of high speed collision, even if a passenger seat is occupied, if there is no high speed collision. If there are high speed collision and passenger seat is unoccupied, the airbag should not be deployed. Right. So for this problem, you need to create a single combined truth table with all the available sensor inputs and actuator outputs for all the 6 requirements together. Some of the truth table entries will be don't care state represented by a cross. For this problem, assume that these 6 requirements together constitute a complete system. So it's a very simplified version of the actual real life problem, but assume this for now. A simple warning for you, that is, if you do not use a don't care condition, you could end up having a large 1024, because that's 2 to the power 10. We have 10 sensors, 10 inputs. Every sensor has 2 options, so that is 2 to the power 10. That is 1024 rows of truth table, which is absurd. Write a C program using Boolean logic concept and tools learned in the class to materialize these 6 requirements. Use if then else structure to do this. Submit the code and your executable. A basic code framework is available to you. The file name is lab1prob3framework.c. Here we have the, so if you list the file, you will see there is a lab1 prob3 framework, and here you can see the code. So you might have to change in control action, you might have to change in the main, in different places. Also submit your version with some sample input and output, lab1 prob3 input.txt named and lab1 prob3 output.txt, so you can run your code and see the outputs like that. For those who choose to use console instead of file IO, you can simply copy the input and output traces from Linux console and paste it to a text file for submission. So these are the two problems that is part of the problem 3. Then we have problem 4. In this problem 4, what you need to do is you realize you're just wasting a lot of hardware and memory space to use separate integer to represent the sensor output and actuator input states. As you get more experienced and confident, you decide to improve your code to save space. You realize this because we're using an embedded system. This has very small memory footprint of only 256 bytes sometimes compared to gigabytes of RAM in traditional desktop system. So each sensor input or output only has 2 possible values, that is 0 or 1, high or low. So we can fit every sensor in 1 bit. And since we have only 10 sensors, we can fit all these 10 sensors in one variable of 32-bit. So for example, bit 0 can represent DOS sensor, bit 1 can represent DSBF, and so on. Similarly, we can have our actuators also represented in 1 byte, 132-bit data variable. So we have bit 0 representing the bell actuator, bit 1 representing DLA, and so on and so forth. So only 32-bit, that is only 4 plus 4, 8 byte data that can be used to encode both the sensor and the actuator instead of using 10 plus 4, like 40 bytes of data. So a global integer variable named sensor inputs with the following sensor input encoding can be used. Again, a global integer called actuator outputs with the following with the actuator encoding that is given here can be used to save some space. And we can set each bit to 0 or 1, and based on this each bit 0 or 1 we can compute our logic of the actuators. So to set each method we will need to do some bit masking. Bit masking uses a combination of logical operations and shift operations to allow the users to set or reset a corresponding bit. So we have given you some example here in the bit masking sample.c and also in the lab1 prob4 hint.c to show some examples, and also in the lab appendix B also has some explanations on how these things work, like the bit masking techniques work. So for this problem you have to write a C program for the control system which uses only 8 bytes as opposed to like 40 bytes that you have used previously. And the program should work in the same manner as the code written for problem 3. You must use bit masking to be able to accomplish this. Use the framework that you used in problem 3 as the basis of this program as well. To improve on top of this problem, when you wrote this code, you also need to write some patterns like 003, 01F, etc., etc. Keeping track of these patterns can become confusing very quickly. To help replace such patterns, you could use some named data type or enumerated data type and assign them a name to each pattern. So you need to explain in a couple of sentences where and how enum could help. Enum is a specific data type of enumerations, could help improve the readability and maintainability of your code. You can also do this with C macro. So these are the two parts of this problem. So 15 plus 5, 20 points that you can get for problem 4. For problem 5, that is the last problem, you try to release this code that you just wrote in problem 4, but some software tester rejected your code on the ground that this is not safe. Why they did not make it safe or deem it safe? Because you need to see, you need to activate the brakes within a specific time, for example 50 nanoseconds of pressing the brake pedal. But according to the tester, your program is unable to respond that fast. So you have to measure the execution time of your code to estimate how much faster you have to run. To measure this time of execution, like how your code is executed, you can use the lab 1 problem 5 framework.c that is given. And for this problem, you have to measure the execution time in both the CentOS and the Red Hat machine. Using the framework, you need to insert your code within the framework to measure the time in the place as indicated in the code file. So here we have the lab 1 problem 5 framework. Here you can see in the main file we have some functions. Clock get time, that is part of the real-time library. Clock get time, some diff to find the differentiation, like to find the difference between these time 1 and time 2. And then there is another library function, clock get res, and then we have some function to read from the input interface, take the time, to the control action, take the time, write output to the output interface. And finally this will print some information. So we don't need to change anything in the mail in most cases, and you can just change these functions, the control action, read input from input interface, write output to output interface, write down your code, and measure the time will be measured using the real-time library. So since these functions here, like clock get time and calibration time, like these functions at line 86, line 87 or line 88, they require some different library, so we need to provide that link to that library. So here, as you can see, we provided the instructions to add that library during the link time using gcc file.c -l rt. Here rt is the library and -l is for linking that during the binary linking time. So the output will be linked with this library. So you have to submit the modified code which has both your code segment and time measuring instrumentation portion, and also you have to submit the outputs generated by both machines. So to measure the time, insert your code in the framework, compile using these LRT options, run the executable, and executable will report the execution time. You have to similarly measure the execution time for the code that you have developed for problem 3, which used 40 bytes of data, and you have to submit the outputs generated by both machines, that is the machines we have the CentOS 7 and the Red Hat Linux system. Finally, you have to write whether your solution for problem 4 run faster than the solution for problem 3. Why or why not? You have to explain that. So these are the problems that you have to do for problem 5. Solution you have to do for problem 5. So these are the main problems, and now we'll go to the appendix. Here we have provided you some examples on how to compile and run C programs using GCC. We're assuming that you have a Unix compliance system where you can check whether GCC version is there. If you do not have a Unix compliance system, you can still use GCC. For example, in Windows, you can download the minified GW software, or you can install GCC as part of the Visual Code Studio. These are explanations given, some links are given, so you can go through them and find out whether GCC is installed using checking the GCC version. So for example, in this case we have GCC 9.4. you can try to get some other version of GCC as well. As long as you run with the GCC stable version, you should be fine. And then you can write using your favorite IDE writing software to create a new file with hello world code, and then compile this file with these options. So here is one example case where we try to use GCC to compile example.c file with some options. For example, we have enabled all the warning flags, like -w is for warning, and then all is for all the warnings. You can see the list of warning options that you can use for your convenience in GCC. And we have used -g option to save the debug flags, debug variables, which we will use later on our lab to analyze the binary program. Then we have provided the name of the file that we want to compile, that is example.c, and -o is the parameter. There are different parameters which gives us the, for example, the -o takes one variable which is example.out, and the output of this compilation will be saved to example.out. So our executable will be named example.out instead of the default name a.out. If you do not provide a minus o some name, then the example will be compiled and the output file will be named a.out, which is the default name. So we can change that with any name that we want. So this will create an executable, and once we execute ./example.out, the output will be hello world as we have written here. So this is just a simple way of compiling, installing GCC, which would be required throughout this course. So we will expect that everyone has access to GCC on after the first lab. And then we have some explanations about bit masking, some tutorials about bit masking. So bit masking is essentially a combination of arithmetic and logical operations of different data types to manipulate only specific bits of the data. Since every data type in C has different types of different number of bits and bytes in them, and by changing them we can save some space, as we have seen in the problem specification. So for example, we might want to set one bit, like just one specific bit. We can use the OR operation. So table 1 shows OR operation truth table. If we have x and y as input, then x or y is the output. And if y is 1, for example here and here, regardless of the x value, the output is always 1. So we can use this and set just 1 in any bit of x. So for example, in this C code, we first put 1 at ith location. This is done by using shifting. So we left shift the 1 ith bit. So all the bits would be 0, and then all the rest of the bits would be 0. And then if we OR that with the data, then we get the ith bit of data as 1, because ORing with 1 would make that bit 1 as well. So this is called setting the bit. So this is one example that we can use. However, this code might not be functional for many cases. There might be some cases where this code might not work properly, so you need to take care of that. But this is some basic to begin your work with, so you can develop on top of this as well. Again, we have negating bits. So for example, we can use the tilde operation to negate or do a not on any of the data type. For example, here we have a simple code, unsigned integer data, that is 0x55. So the bit pattern is 010101. Then we do a tilde, data is equal to not data, and then we try to print the data, and the bit output should be 0xAA, where the bit pattern is 101010. So this is using the negation, because once we do negation, then the bit becomes 0, bit becomes 1, and bit becomes 0. Here what we can see here, the tilde operation is done on the whole data, so essentially all the bits are affected. So we might want to disable only one bit, that is we might want to set any one of the bit to be 0, and we can do that using resetting bit technology, resetting bit technique. So we can do that using AND operation and a combination of the tilde operation. So what we need to do is we need to clear any one specific bit of the data. To do so, we can use the AND logic, because when we do AND and we AND it with 0, then regardless of x and y value, x value of 1 or 0, we still get output as 0. So if our required bit location we have a 0 and all the other bits are 1, then we will get 0 at that bit. So for example, here first we set a bit pattern to be 1 at the ith index, and then not it. So essentially we will set all the other bits as 1 and that bit as 0, and then we AND with the data that we want to change. So in that way, the data at ith location will have 0, and all the other location will have whatever it had before. So it will reset only the ith bit. So that's how we can reset ith bit. So this is again works with some caveats. So I will not discuss those for brevity, but it will work for the lab at least. We can use it for the lab, and we can build on top of this. And then we can have XOR. XOR is just used to flip the bit. So essentially we can, if we have 0 here and then we try to XOR it with 1. So for example, x is 0 and XOR it 1, the x XOR y would be 1. Again, if we have x bit as 1 and XOR it 1, the x XOR y answer would be 0. So XORing with 1, we get the flipped bit. So if the initial bit was 0 and we XOR it with 1, we get 1. Initial bit was 1, we XOR it with 1, we get 0. So we can use this idea to use XOR and flip any bit at any specific location. So there are other techniques as well which you can use, but these are all part of the bit masking techniques that we can use to manipulate different bits of any location of the data. So that's it for today. If you have any questions, feel free to ask. We will try to answer those questions. You can always contact me at farabi@tamu.edu, and yeah, and during the office hour you can come to my lab room, that is 264 at Peterson. Thank you for your time. Have a great day.